I just want to be on his screen. I'm not on the screen at the moment. Yeah, that's fine. That's fine. I'm just there we go. That's good. Our second last speaker for the conference is Eugene Bilokopytov, who will be joining us online and will be speaking on various characterizations of band projections. Please proceed, Eugene.
Thank you very much. And I wish I could join you not online, and I almost made it, but the officers didn't allow me to. In fact, they didn't even allow me to catch my flight in Edmonton, so I had to do some extra work to get at least to Paris, but then from Paris it was a dead end, couldn't get to Tunis. Okay, so anyway, my talk today will be about basically what it says it will be. It's about various characterization of projection bands. So they will be, I hope they will be truly diverse, but that you will be the judges of that. So let's start with some preliminaries, which I'm sure most of it you already saw even on the previous talk, for example. So we will be talking about a vector lattice, and a solid set is such that if an element of a vector lattice is dominated by an element of a set, then it is in set, and then it's always a balanced set. And we will now consider a few more different subsets of a vector lattice. So, for example, a sublattice, which is always a linear sublattice, is a set which is closed with respect to the absolute value. In other words, the inclusion into the big lattice is a homomorphism. An ideal is a sublattice with this additional requirement that if an element is dominated by an element of an ideal, it is an ideal. And this is the same as to require a subspace, linear subspace to be solid. And also this is the same as to require the set to be a kernel of a homomorphism. And projection band is an ideal with this additional property that it is equal, that the entire lattice is equal to the direct sum of the ideal and some other ideal. So the direct sum meaning that they do not intersect. And then in this case, it is automatic that this other ideal is the disjoint complement. And in fact, we have an equality, or rather isomorphism of the original vector lattice and the direct sum of the two ideals, but not within the original lattice, but rather a sort of external direct sum. So in this case, a vector lattice decomposes as direct sum of two other lattices. So in my opinion, this is the principal reason why the projection bands are important. So now let's, so my talk will be about different ways to guarantee that a certain ideal is a projection band. Okay, so an example, which again, probably you already know, is that in C of X kind of space, space of continuous functions on a topological space, closed ideals are of the form like this. So these are functions which vanish at a certain closed set. And in particular, they will be projection bands if and only if the set is closed. So this is kind of similar intuitively, right? So projection band is a kind of a unit of decomposition of a vector lattice, and then a closed set is a unit of a decomposition of a topological space. Okay, and the intersection of any sets of ideals or sublattices is still ideal and sublattice. And in particular, the smallest ideal which contains a given element, you can construct it in this way. It's a union of this expanded intervals, and if it is equal to the original one, we will call E a union. All right, so a property which will kind of inspire us later on, or soon, very soon, is that usually if you have, for example, a Banach lattice and you take a principal ideal, usually it's not going to be closed. So let's keep it in mind, just a few moments. So another fact that we need is the Kakutani-Crane representation theorem. It also is known by other names. So it says that if we have an Archimedean vector lattice, then every principal ideal is essentially a dense sublattice of C of K. Right. So for it, we can find the compact Hausdorff space. For every element E, we can find the compact Hausdorff space KE, such that the principal principal ideal of E is isomorphic to a denser lattice of C of K. And in the case that it's not just a denser lattice, but actually the entire C of K, we will call F uniformly complete. We will also call a subset of sublattice uniformly closed if the intersection with every principal ideal is closed with respect to the topology inherited from C of K. We will later give a different point of view on the concept of uniform completeness and uniform closeness, but for now, this will be the definitions. And here's the first sufficient condition of projection band. So let's say that you have a Archimedean and uniformly complete vector lattice, then an ideal which is countably generated. So there is a countable set which such that our ideal is the smallest one containing this countable set. So if this ideal also happens to be uniformly closed, then it is a band, then it is in fact a projection band. So for this kind of ideals, to be uniformly closed, to be a band, and to be a projection band is the same. So I haven't given a definition of a band, it will come later, but I'm sure again, all of you know what it is. Okay, so now let's consider another characterization. I call it a horizontal characterization because it deals mostly with this, not with the original vector lattice itself, but rather with a kind of a derivative object, which is the collection of all ideals of our vector lattice F. So it's easy to see that it's a complete lattice with respect to inclusion. So this means that every collection of ideals, for it you can find the smallest ideal, which is the intersection, which is contained in each of them, and the largest ideal, which is slightly less obvious, but still it is possible to find such an ideal. And moreover, this lattice has a maximum element and minimal element, maximum being the original lattice and the minimum being the zero set. Set consisting of only zero. So additional property is that disjointness understood in different ways is sort of consistent. So if you have two ideals, then they're disjoint in the sense that their intersection is the minimum of IF. This is if and only if every individual element of E is disjoint to every individual element of H. And another fact is that if you want to find the supremum of E and H in the lattice of ideals, you simply take the sum. And the last can be also extended to any collection of ideals. So if you have a collection of ideals, then to take, if you want to find its supremum in IF, you simply take a direct sum. You simply take their sum in this sense. So you take all finite sums of elements of the ideals in your collection. Another property of this lattice is that it is distributive, but in a slightly asymmetric way. So the intersection distributes over some in the finite case, right? So if you have three ideals, then H plus intersection of E and G is the same as you first add E and G to H and then intersect them. And the sum distributes over intersection, infinite sum distributes over intersection. So this means that if you have a collection of ideals, you take their sum first and then intersect with some other ideal H. That would be the same as if you first intersected H with every element of your collection and then took their sum. So of course, a natural question would be, to which extent can we also have infinite distributivity for the intersection? And we will answer this question in a moment. So before, let's also observe that, remark that projection bands are precisely the complemented elements of the lattice IF. So let me remind you that complement of an element in a lattice with the maximum and minimum is another element, such that intersection with the original element is the minimum, and or rather infimum with the original element is the minimum, and supremum with the original element is the maximum. right? So the definition of a projection band precisely says that it is the complemented element of the lattice of all ideals of a vector lattice. So it is not hard to show that a complemented element of a distributive lattice form a Boolean algebra, which is a sublattice of original lattice. So in particular, projection bands form a sublattice of the lattice of ideals of a vector lattice, which is a Boolean algebra. Another property which is very easy to prove is that being a projection band is a local property of sorts. So an ideal is a projection band if and only if its intersection with every principal ideal is a projection band in that principal ideal. Okay, so this is really easy to show. And so from now on, we will only talk about Archimedean vector lattices. And here comes the first kind of non-trivial characterization. So an ideal of a vector lattice is a projection band precisely if the intersection distributes, infinite intersection distributes over some with this specific ideal. So this is to say that if you have any collection of ideals, then you will have an equality between the sum of H and intersection of this collection and intersection of the collection of the sums of agent elements of your collection. And the proof is kind of, it's not very difficult, but it's not very simple either. And also it goes through the Crane-Kakutani representation theorem. So I don't know, somehow intuitively, I should be easily proven and should not even be called a theorem. So I have a question which looks very simple, but I couldn't answer it. So if it is answered in the positive, then the proof of the theorem becomes very simple. So here's the question. So let's say you have an ideal and you have some positive element of that ideal. Can we always find another ideal of the vector lattice which does not contain our chosen element, and such that the sum of this ideal with the original one is the entire lattice? Okay, so I think it looks very simple, but somehow I couldn't prove it. Perhaps it could be perhaps it could be something to think about for the rest of the talk. If it's not, sorry. Okay, so if this question is answered in the positive, then it's kind of easy to prove this theorem. You just take the collection. So for every element H in H, you just take a collection of all such J's, and then the intersection will be disjoint from H, but on the other hand, this intersection on the right-hand side is going to be equal to F. Okay, so now I have some room on my slide, so let me give a definition of a band. So a band is an ideal such with the property that if there is a supremum of any collection, any subset of this ideal, then it has to be also an element of this ideal. And and every disjoint complement of any set is a band, and in Archimedean vector lattice, a band is a double disjoint complement of itself. And every projection band is in fact a band. Okay, so next, let me present what I call a vertical characterization, because it will sort of be about how big a certain set is in the magnitude rather than in the width. So perhaps this is too vague, but let me now present a lemma which was helpful in this in the proof of the theorem. So the lemma combines ideas which appeared in many papers. So I think I mostly was inspired by the work of Wechsler and Geller from 72, Abramovich from 73, and Bernau from 75. So I think that I managed to kind of extract everything there was from this idea. So here's the lemma. So let's take two positive elements. Let's take an increasing sequence, and let's take an ideal generated by this increasing sequence. Then you can find another sequence, fn's, and let's denote their partial sums by gn's with the following properties. So first property is that the sequence of n is almost disjoint. So the only way two elements are not disjoint is that if they are adjacent. The second property is that if you subtract the partial sum for a greater index from f, it will be disjoint with all the previous fn's. So the next property is that gn's, these partial sums, approximate f almost as good as hn's approximate f. So we had an increasing sequence hn's. So you can think of it as some kind of approximation of f. Then the gn's that we constructed approximate f almost as nicely as hn's. So the only additional summand here is 1 over n times e. And the final property is that if some element is greater than all of these partial sums, then it kind of makes f disjoint with h. So if you subtract g from f and took the positive part, it will be disjoint from f, disjoint with h. Okay, so perhaps it's not going to be immediately clear how this lemma is used in the theorem, but I just think that it's potentially very useful. I think it could be applied in many cases when you need to construct some disjoint. So in particular, it helped me to prove the following theorem. So for an ideal, the following properties are equivalent. First one is that it is a projection band. The second one is that the order boundedness with respect to f is the same as with respect to h. So this means that if you have an order bounded set, a set which is order bounded in f and contained in h, then it is in fact order bounded in h. So it is order bounded with respect to order structure of h. And in fact, it is enough to consider this only for disjoint sets. So sets consisting of mutually disjoint elements. Okay, so I call it a vertical characterization because it deals with order boundedness, which if you imagine vector lattices kind of spaces of functions is sort of like a vertical property. So it's below something and above something. So that's why I call it vertical. Okay, so let me briefly review projection property. It's for the most part, it's nothing really new, but I thought that it could be interesting to some of you. So again, bands can be described precisely, exclusively in terms of the lattice of ideals IF, right? So similarly to how projection bands were the complemented elements of IF, the bands are the pseudo-complemented elements of IF. So this is again a term from the abstract lattice theory. Pseudo-complement of an element of a lattice which has an infimum is the largest element which is disjoint to the original one. So it's easy to see that the band is precisely that. So again, like I said, for the projection bands, we don't really need to look at the ideal itself. We only need to look at it as an element of the lattice of ideals. So other examples of this kind of properties would be, of course, prime ideals, right? You don't need to know anything about the prime ideal itself. You only need to see how it sits in the lattice of all ideals. And maximal ideals are literally defined in these terms. So it would be interesting to think what other properties of ideals could be seen from the lattice of all ideals. Okay, so anyway, again, this is a property of lattices with a certain addition. So these are properties of distributive lattices is that all pseudo-complemented elements form a Boolean algebra, and it is a sub-semi-lattice of the original lattice with respect to the meet operation, infinitum, but not necessarily with respect to join operation. So intersection of any collection of bands is band, it's well known. And the vector lattice is said to have projection properties. Every band is a projection band. So a slightly weaker condition is if every principal band, so a band generated by a single element is a projection band, then F is said to have principal projection property. And a property which I don't think I've ever seen explicitly mentioned. So if every countably generated band happens to be a projection band, we will say that the vector lattice has a sigma projection property. So these are abbreviated as PP for projection property, PPP for principal projection property, and sigma PPP for sigma projection property. And you could consider the sort of domain of principal projection property defined in the following way. So let's consider all such vectors such that the principal ideal generated by this vector has a projection property. So it's not very difficult to show that this is an ideal of F, which itself has a projection property. So this is, of course, the largest ideal of F that has a projection property. And the same holds for principal projection property and sigma projection property. And just in case, let me mention that this ideal does not have to be closed in any reasonable way. It is not uniformly closed. And the counterexample would be C. Okay, so yeah, so variant of theorem of the vertical characterization of projection bands is the following, that a vector lattice has a principal projection property if every order bounded disjoint set has an upper bound which is contained in the band generated by the set. And the same holds for sigma, but then we will have to take, it is enough to only take countable G's. So in particular, from this it follows that disjoint sigma completeness implies disjoint projection property. So this was done by Wechsler and Gehler. So disjoint sigma completeness or disjoint completeness means that every order bounded collection of disjoint elements have supremum, and the same for sigma. But so if we only talk about countable sets, then it's sigma. Okay, and let me now review a well-known result by several people. So in particular, Nakano, Luxembourg, Zanin, and Wechsler. So if you have a compact Hausdorff space, then the following conditions are equivalent. One is that it is extremely disconnected. So this means that the closure of any open set is open. Another one is that C of K is order complete. Another property is that every dense sublattice of C of K has projection property. And the last one, that C of K contains a dense sublattice with projection property. So notice here that existence and every are equivalent, in fact. So in my opinion, so the reason why I decided to bring it up is because I don't think this is spelled out anywhere explicitly. So again, let me stress that if you manage to find the dense sublattice of CK, which has projection property, then K is automatically extremely disconnected. And if that happens, and you took any dense sublattice of C of K, it will have projection property. So for principal projection property, situation is different. So a compact closed-door space is totally disconnected if and only if C of K contains a dense sublattice with principal projection property. So here only existence is equivalent to total disconnectedness. So, but perhaps a better analog of this property would be the following. And it was kind of also proven by the same people, but not explicitly. So for a compact closed-door space, the following conditions are equivalent. One is that it is basically disconnected, meaning that the closure of any F sigma open set is open. So not any open set, but only any F sigma open set. So this is equivalent to C of K being sigma order complete. That is also equivalent to C of K having principal projection property. And now we have this similar characterizations as to the extremely disconnected case, but now we have to take sigma pp. So every dense sublattice of C of K has sigma pp, or C of K contains a dense sublattice which has sigma pp. Okay, so for PPP, the situation is different. But for sigma pp, it is similar. And the corollary of these two results is that a vector lattice has projection property if and only if all of its Crane-Kakutani spectrum, so these are the K-is which appeared in Crane-Kakutani theorem, are all extremely disconnected. So this is if and only if. And the countable case is that F has a sigma projection property if and only if the Crane-Kakutani spectrums are basically disconnected. So this gives kind of, again, what I would like to call a horizontal characterization of projection property. So it is characterized in terms of the spectrums. And the corollary of that is the well-known result by Luxemburg and Zanin is that a vector lattice is sigma order complete if and only if it is if it has principal projection property and is uniformly complete, or is order complete if it has projection property and it's uniformly complete. Okay, so this is the end of the first half of the talk, in which the characterizations were kind of algebraic in nature, if I may say so. And now we will move on to the characterizations which are more topological. Okay, so for this, I will need to introduce the concept of locally solid convergence. So I know that some of you have been to my talks and you have seen these definitions, in some cases more than once, so for that I apologize. But I need to introduce this in any case. So a locally solid linear convergent structure on a vector lattice is some kind of device which decides, I call it adjudicator, if a given net converges to a given element of F. Okay, so you give this arrow a net and you give it an element, and this arrow tells you if it converges or not. And it has to satisfy certain axioms. So one of them is that if a positive net converges to 0 and you have a quasi-subnet of it, then it also converges to 0. So I decided that it's probably not wise to give a definition of what a quasi-subnet is. It's just something slightly more general than a subnet. Okay, so you can just think of it in terms of a subnet. So if a net of positive element converges to 0 and you have a subnet, then it also has to converge to 0. Another element is that if you have a net which converges to 0 of positive elements, and you have a net which is dominated by this net, then the dominated net also has to converge to 0. So this is what makes it locally solid. So next up is additivity. If you have two nets of positive elements which converge to 0, then their sum also have to converge to 0. So linearity is accounted by this axiom, is that if you take a positive element and keep dividing it with n, it will converge to 0. And finally, so the first four axioms only involve positive vectors. So we kind of extend this to the entire F by demanding this last property that a net converges if and only if the absolute value of the differences converges to 0. So this absolute value of the differences moves everything from F to the positive cone, where we have these 4 axioms. All right. So one of the main differences between convergent structures and topology is that the closure is not closed. So for that, we introduce a new term we will call the set of all limits of elements of a set A, an adherence of A. And I use this notation, kind of A like a closure, but with 1. And the set is closed if its adherence equals to itself. And the closure is the intersection of all closed sets that contain A. So you can actually show that the closure and the collection of closed sets, they do form a topology. But in this talk, we will mostly ignore this topology and only work with the original adherence. So this closure could be obtained by iterating the adherence. So first we take all the limits and we get A1, then we take all limits in A1, we get A2, and then we run this procedure transfinitely. And for a large enough ordinal, it will stabilize at the closure of A. So if you have a net, we will call it Cauchy if the net of double index net of the differences is convergent to 0, and completeness means that every Cauchy net has a limit. Okay, so these are the definitions associated to locally solid convergence. Now let's derive some properties and consider some examples. So a linear topology on a vector lattice is locally solid precisely if it generates a locally solid convergence. So this is not very difficult to show. So in particular, every Banach lattice, so the norm topology induces a locally solid convergence. Okay, so some properties here. The linear operations as well as lattice operations are all continuous. So continuous means that they preserve convergence of nets. So next up, the Hausdorffness of this convergence is characterized by the fact that singleton 0 is closed. So Hausdorff means that the limit of any net is unique if it exists. And few more properties. So if we assume that F is Hausdorff, then automatically the vector lattice has to be Archimedean. It has to be infimum of 1 over NF. And the limit of a monotone net, if it exists, has to be its extremum. So for example, if you have a net which decreases and simultaneously converges to 0, then 0 is actually the infimum of the net. Another useful fact is that adherence and closure preserve certain nice sets. So adherence of a sublattice is a sublattice, closure of a solid is a solid, and so on. And an additional useful property is that the adherence and closure kind of commute with taking the positive part. So if we have, for example, a solid, and we can then either first take adherence and then take its positive part, or we could first take the positive part and then adherence. Okay, so now we can state yet another characterization of projection bands, now in terms of a convergence. And it is the following, that if we have an ideal, then its adherence is a projection band if and only if for every positive element F, you can consider this net. So this is an increasing net indexed by itself. So yeah, it has to converge. If it converges for every F, then the adherence is a projection band. And of course, the limit of this net will be the projection of F with respect to this band. So the proof is kind of similar to the proof of the special case, which is well known. When you take the order convergence, then this adherence is simply the band generated by H. So it will read as follows. So For order convergence, we will say that if H is an ideal, then it generates the band that it generates as a projection band, if and only if the set has a supremum for every f. And the proof is, for the most part, it exploits the similar idea. Okay, so now let's consider a few more examples of locally solid convergence. So one example are the locally solid topological Lie spaces, also Banach lattices. So one more example is a relative uniform convergence. So it's defined as follows. So for every positive element E, we consider the Minkowski functional of the segment from negative E to E. We will also say that it's equal to infinity outside of the principal ideal generated by E. So then we will say that a net relatively uniformly converges if it converges with respect to this Minkowski functional for some element E. So in terms of Crane-Kaputani representation, this simply means that you mapped everything inside of C of KE, and there it converges uniformly. So a useful fact is that, or perhaps it's not all that useful, but it explains why Banach lattices are so nice, is that the Banach lattice topology is in fact the strongest topology, weaker than relative uniform convergence. So it's a topologization of the relative uniform convergence. And what I was saying at the beginning, the uniform completeness is in fact completeness with respect to relative uniform convergence, and uniform closeness is closeness with respect to relative uniform convergence. So this is not entirely obvious, but it's not very difficult to show. And for the most part, this was only to exemplify the notion of locally solid convergence, which is not topological. Okay, another example of such convergence would be the order convergence. And again, I decided not to give a definition because definition is hard to digest if that is the first time that you see it, but most of you probably know what order convergence is. So let me just say that this is, you can show that it is the strongest locally solid convergence in which every monotone net converges to its extremum. So if you start with the premise that in your convergence, every monotone net has to converge to its extremum, or just decreasing to zero nets converge to zero, then you can show that you get at least, or at most, order convergence. And now we can present another characterization of projection bands in terms of order convergence, and it reads as follows. If you have an ideal such that order convergence on this ideal coincides with the order convergence of the original lattice restricted to H, this is equivalent to the fact that H is a projection band. So many of you probably know a similar fact about unbounded order convergence, which says that a sublattice is regular if and only if the restriction of unbounded order convergence of the big lattice to it coincides with the unbounded order convergence generated by it. So for ideals and order convergence situation is quite different. So in most cases, order convergence will be different. So the only way it is not if it's a projection band. Okay, so this was a characterization of projection bands in terms of order convergence. Now let's move on to characterization in terms of the unbounded modification. So what is unbounded modification is, this is a convergence which is obtained from a given locally solid convergence in the following way. So we start with the convergence eta, and we define U theta, but by defining the convergence to zero on the positive cone, right? So we say that f alphas U eta converge to zero if the truncation, this kind of truncation converges to zero for every possible, if we truncate with every possible positive element. So you can show that this is a idempotent operation, and there are some properties which were investigated for the case when you start with the norm convergence on a Banach lattice. So it's not very hard to show that if you generally start with the topological convergence, then the unbounded modification is still topological. So in case you start with norm, you get unbounded norm convergence. So in LP spaces, this will be exactly convergence in measure. And there are just, this is just a selection of two properties of U and topology. So first one is that the unit ball of your Banach lattice is complete with respect to U and topology. If and only if your Banach lattice is a KB space. So the definition is that every increasing sequence in the unit ball is convergent. There are, of course, other characterizations in terms of U and topology, but this is a random, nice one. And another nice property of U and convergence is that every UN null sequence, which is normalized, contains a normal Dijon sequence. So there is a Dijon sequence which is co-asymptotic with this one. So we will need this property. This is just a demonstration of why unbounded norm convergence is useful. Okay, so similarly to how we defined the locally solid convergence, unbounded modification by truncating with every element, we could instead only truncate with some selection of elements. So let's say we have a subset of a positive cone, and then we will consider unbounded modification with respect to A, defined in the same way, but only when we take the truncation with respect to by elements of A, and not by every positive element. So few properties of that. So first one would be that this is the weakest locally solid additive for linear convergence, which is stronger than the original one on the intervals defined by elements of A. And another property is that if you have two ideals and you consider unbounded modification with respect to these ideals, then you will have the following: that if you take unbounded modification with respect to E and then unbounded modification with respect to H, that would be the same as if you took unbounded modification with respect to their intersection. So in particular, the operation of taking unbounded modification with respect to E is idempotent as well. So now let's assume that our original convergence was topological. So there is an auxiliary result that if you have a fixed net, then the collection of all elements with respect to which you truncate the original net and the truncations converge to zero is a closed ideal. So for that, we actually do need to know that the convergence is topological, or at least have some kind of diagonal property. So it's at least I am not able to prove it for general convergence. And from this, we can derive the following result: that the unbounded modification with respect to A is the same as the unbounded modification with respect to the closure of the ideal generated by A. So in particular, if you happen to have an element in your vector lattice such that the ideal generated by this element is dense, then the unbounded convergence is described in this very simple way. So a net unbounded converges to zero if and only if its truncation with respect to this special element A, H converges to zero. Okay, so if you have a sublattice, you can consider two different topologies or convergences. So first you restrict your convergence from F to E, and then you take its unbounded modification. And the other topology is that you first take its unbounded modification on F, and then restrict it to E. So the first one that I mentioned is this one, and the second one that I mentioned is this one. So it is not very hard to show that this convergence is going to be stronger than this convergence. So the natural question is, in which cases they are equal. And Kandich, Marabek, and Troitsky in 2017 proved that essentially they prove that if you have a sublattice such that the closed ideal generated by the sublattice is a projection band, then the two topologies coincide. So the proof is not very difficult, and but it works for specifically topological convergences because we need this result. So, but they considered topological convergences anyway. So for them it was enough. So they asked whether the converse to this statement is true. So is it true that, or perhaps to which extent the converse to this is true? So if we know for a sublattice that the two convergences coincide, what can be said about the sublattice? And the last result of my talk is the sort of partial converse to the previous result. So if we have a complete locally solid convergence, so we don't actually need it to be topological, and we have an ideal with the property that the two convergences defined in the first line coincide, then the closure of this ideal has to be a projection band. Thank you.
Oh. Okay. Thank you very much for your interesting talk. Are there questions? Then let's thank our speaker again. And thank you for your effort to join us remotely and in person.
I don't know if he